Hey there. Let's do a quick recap of what we talked about earlier with the sum. So we said that when we have our graph with a curve, we can use a sum notation to decide or to evaluate our estimate of the curve. With from A to B, we had a few variables. We had n, which was number of subintervals that we were going to use. We had A and B, which were the bounds. And then both of these together gave us the change in x. We had I, which was part of the sum in I. And finally, we had f of x. And since the formula to get the area of one rectangle was base times height, that would be f of x times change in x. Oops, that's chemistry. Change in x. And to do it for every single one of them, it would be n I equals 1, and it would be f of x I times change in x, where xi was equal to, depending on which one you wanted to evaluate, the right hand, left hand, or midpoint, it would be a plus change in x times I. And this would be the right hand. The left hand would be a plus change in x times I minus 1. And finally, the mid would be a plus change in x times I minus 1/2 change in x. And yeah, that's what it would be. So what you have on the inside is sum base times height, and then the x that you're evaluating depends on which one you're doing. And so let's start applying that to some actual equations. Okay. I'm hit record. Yeah, hit record. Okay. Let's start with an easy one. X squared e to the x. F of x equals x squared e to the x on the interval 0x6. Okay, so this means that, let's write out the variables. A equals 0, B equals 6. How many subintervals did it say? Uh, it said, um, it actually doesn't say, but I want to make something up. Uh, 5. 5 subintervals. So now, our function is that what we're going to calculate is our change in x. Our change in x is going to be equal to 6 minus 0 over 5, 6/5. And now we're ready to make our limit. Or not the limit. N, I equals 1. N gets replaced with 5, so as I goes to 5. And then f of x is this. So we have to figure out what x is. So we're going to do it from the right hand for simplicity's sake. And x is going to equal a, which is 0, plus I times the change in x, which is 6/5. So it will be 6i over 5 equals x. Yes. So 6i over 5, plug it in for x, x squared, times e to the power of 6I over 5. And then all of that times 6/5. And boom, we have our sum. We can plug this into our calculator and it will return to us the value that we want, which is the area under the curve of that. Now, I want to make one more observation here before we start getting into the more complex version of the sum, which involves a limit. Let's say you have a curve that goes underneath the x-axis. X. What is the area under the curve? We know that here we've got area, 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 and area, area, area right here. What do we do with this? Because this is where the x-axis is, and there's stuff underneath it, we know, but we can't exactly do this because this is an infinite area. What we do is we calculate this as our new area. And it's going to be a negative, which means that the technical area under this curve is going to be this, A plus B, C is going to be A plus B minus C equals the area. I'm going to put that in quotes because it's not actually the area. This is when we start getting into less of the definition. Ooh, I got a notification. Dang, it's still not out yet. Okay. It's not so much the area anymore, it's like its own thing, and this is where we start getting more theoretical as opposed to let's apply our knowledge like we were before. So now that we have that, let's start talking about how to actually evaluate one of these sums to get the true area, because so far we've been doing estimates. So I mentioned earlier, so yeah, it's not paused, that n is the amount of subintervals there are. N is the number of subintervals. Subintervals. And I can have like 3 or 4 subintervals, and I can divide those in 2, and so forth. Now, I want you to know that as my subintervals get smaller and smaller, the area I lose on an estimate gets smaller and smaller as well, because my change is so small that it's infinitesimally small. So, this is the idea of a limit, if you remember back to what we were talking about a while ago. We are now going to involve a limit in this. And so what would be the ideal amount of subintervals to get to this idea of so close to perfection that there is nothing lost in the estimate? It would be n equals infinity. So when we have infinite subintervals in between a and b, we know that our sum is going to approach what we want. So let's redefine our variables. When we have our graph, I'm just going to draw a quick graph over here for reference. B, n, starting out, is going to be equal to infinity. In addition, a is going to be equal to a equals a, b equals b. It's just what they are. Those are the domain. And from this, the change in x, which if you remember is b minus a over n, is going to be equal to b minus a. I mean, that was redundant. B over I minus n. Because we have infinite subintervals, a finite distance divided into infinite pieces. So we're also going to have our f of x, and that's just going to be whatever f of x is. And then the same thing happens. We just construct our sum. In I equals 1, f of x is going to be a plus change in x times I. So it would be b minus a over times I over n. Times b minus a over n. So this is what it is, but because n approaches infinity, we now add the limit as n approaches infinity, sum of this. So it looks really complex, but in reality, it's a bit simpler than you would think. So we can start by simplifying it by saying that this in here is just f of a plus change in x I over n, which is change in x, times change in x. Now notice it is still height times the base, it's just now the amount of subintervals is different. And we can evaluate it pretty easily. Now how do we evaluate it? Well, first, this is kind of general idea. Some problems are just going to ask you, hey, find the, like, given a function, create this limit summation and stop there, but don't actually evaluate. But I'm going to teach you how to evaluate it right now using an example. Maybe. Okay, actually, first I'm just going to show you how to dissect it, and then I'm going to actually summate it. Uh, so let's say we have 5 sine squared x. F of x equals 5 sine squared x on the interval of 0 to x to pi. Okay, so it's technically going to be right endpoints. Like it's always going to be right endpoints. You don't really get an exception because when you're approaching infinity, right endpoints. So let's identify our change in x is going to be pi over n, because pi minus 0 divided by n is going to be that. Our n is going to be infinity, and our x for the f of x is going to be a, which is 0, plus pi over n times I. So it would be pi I over n. That's fun to say. So now we can create our summation limit. Lim as n goes to infinity, summate n, which is infinity, I equals 1, 5, put that in parentheses, sine squared, x was pi I over n, boom, times pi over n. And this is going to be the answer if it was asking you to do this. So the names of each of these individual things are what they are. What homework am I on? Okay. So the question, wait, what? Yeah, sometimes I'll ask you to go back in time. Don't stress, just do it. Okay, so now I'm going to teach you how to evaluate it. First, no, wait, we're going to do integrals. More notation. So, change in x equals pi over n, we know that. But let me teach you about the derivative notation. Well, I keep that up there. The integral notation. So the integral is this little curve, a to b, and then f of x dx. Okay, so this is the notation at its basic form. The squiggle right here represents both the limit and the sum at the same time. So instead of having lim and sum, I just have squiggle, and a and b tell me the domain that we are on. Easy enough. The dx is just part of the notation. You don't have to worry about what dx means, it's just there. Don't stress. The important part is f of x and a and b. It's a simplified way to say that's what we're doing. So instead of Oh yeah, instead of writing out a bunch of stuff with like, oh, change x times I and then 5 sine squared, it's all implied in this notation when you have x. So the original here was 5 sine squared x. What this would look like, oh yeah, and it was on 0 to 2 pi. This would look like, in reality, pi 0. So it starts from 0, goes to pi, and then it is 0. Oh, then it's the formula 5 sine squared x dx. Like I said, don't worry about what dx is, it's just there for kicks. And there you have it. That's your integral. You can actually plug this into your calculator and it'll work. But what you're going to be concerned with, especially on the exam I have coming up, is converting from this back into that. So let's break it down. From this, I know that my interval, or my a, is going to be 0, and my b is going to be pi, which means that my change is going to be pi over n. So change in x equals pi over n. My function is 5 sine squared over x, and x is going to have to be a, which is 0, plus what I have over there, I pi over n I times my change in x, which is equal to pi over n. So we can erase it and say pi over n. Now there is a connection here. The derivative right here, d of x, is technically our pi over n, just in the notation, we don't actually have to think about it. Like I said, just ignore d of x. Don't think about it, out of your head. So now that we have this, we have now successfully converted our thing into another notation. So it's going to be 5 sine squared pi I over n times pi over n, and it's going to be n I equals 1, lem n goes to infinity. There you go. This is how you convert back and forth. You can see they're essentially the same, just this integral notation is way simpler, and you don't have to think as much. Unless you're trying to convert back to it because you want to evaluate it. So on this exam, they're going to be making us do it the old-fashioned way. I still don't get it. I want my exam grade. Um, it's just converting back, or on the exam, they're going to make you convert from this back into this, or the other way around, just for kicks, and then evaluate the limit using this. And I'm going to teach you how to do that in the next video, how to evaluate your summative integrals, or evaluate your integrals. Anyways, this is what an integral is. That's how to go back and forth. Uh, and yeah, I hope that makes sense.